We are going to do 2 short lessons on parametrics. And the thing you need to know about these is they're really not that hard. It's everything that you've already learned how to do. With derivatives, you just kind of do it twice. Now, obviously, I'm underselling it a bit, but that's kind of how it works. So I need you to have your parametric packet out. I also need you to have a graphing calculator out, or just make sure you pay attention to what I'm doing with the graphing calculator, because that will help you quite a bit as you go through these. So in your packet, I need you to find lesson 1, graphing derivatives and parametric curves, or graphing and derivatives, pardon me, of parametric curves. So on this first one, we got to talk about what the heck are parametric curves. Well, what they are is just regular curves, but instead of x and y being like interdependent on each other, x depends on this other variable t, and y also depends on that variable t. And the easiest way to illustrate this is using a table. So I need you to make a table, and our table is going to have t and x and y, and our x is t squared minus 2t, and our y is t plus 1. Now, for t, it doesn't have to mean time. Sometimes it does, but it doesn't have to. So what I'm going to do is I'm just going to pick some t's, and I'm going to allow them to be negative, because time doesn't always have to be positive. Just trust me on it, okay? So then when t equals negative 2, I'm going to plug that negative 2 into the x equation up there and get 4 plus 4, which is 8. And then when I plug negative 2 into the y equation, I'm going to get negative 2 plus 1, which is negative 1. And then I'm just going to do that 4 more times. So when t is negative 1, I have 1 plus 2, that's 3. When t is negative 1, that's 0. When t is 0, I get 0 for x, 1 for y. When t is 1, I get 1 minus 2, that's negative 1, 2 for y. When t is 2, I get 0 for x and 3 for y. So what that means is it means I am going to draw a curve on a regular xy axis. T is going to effectively be invisible, and I am going to plot the point 8, negative 1. By the way, he will keep showing up. This is Pete. Everyone say hi, Pete. Pete cannot stay away from me when I am trying to work on the computer, so he will probably chew on the cord from time to time or climb in front of the camera and knock it over. All right, so I have to plot the point 8, negative 1. So 8, negative 1 is my first point. 3, 0 is my next point, so 3, 0 would be like there. 0, 1 is my third point. Negative 1, 2 is my next point. And back to 0 and up to 3 is my third point. And notice, this graph is now not going to be a function because it will not pass the vertical line test. And so if I connect the dots, I think it's going to look something like that. And with parametric curves, you put 1 arrow, not 2, you put 1 arrow on there to indicate direction. So this started low and went high, so this is going in that direction. Now, I kind of lied. You can put as many arrows as you want, but they don't go at the ends like you're used to. They go on the curve to indicate the direction of the path. So we would probably draw this like that to show that that's the direction of the path. And there's your parametric equation. All right, let's do another one. It says create a table and graph 2 cosine t and sine 2t. So again, I'm going to make a table. And I have t, x, and y. X is 2 cos t. Y is sine 2t. And because I'm doing sine and cosine, I'm going to use sine and cosine inputs. So I'm going to make my t inputs 0, pi over 4, pi over 2, 3 pi over 4, and pi, and then see if I feel like continuing and see how hard it might be. All right, so 2 cosine t, 2 times cosine 0, that's going to be 2. And sine of 2t, that's the sine of 0, that's 0. All right, 2 cosine pi over 4, that's going to be root 2. The sine of 2 pi over 4, which is the sine of pi over 2, that's 1. Cosine pi over 2 is 0. Sine of pi is 0. 2 cosine 3 pi over 4, that's going to be negative root 2. And the sine of 6 pi over 4, which is 3 pi over 2, that's negative 1. All right, so I kind of see a pattern here. Let's see. Cosine pi is negative 1, so this is going to be negative 2. Sine of 2 pi is going to be 0. And I feel like this isn't hard to keep going, so I'm just going to roll with it so you can see the whole thing. So I have 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4. Down here, this would be cosine in the third quadrant, so still negative. That's going to be negative root 2. Cosine of 3 pi over 2 is 0. Cosine of 7 pi over 4 is root 2 over 2. Times 2 gets me a root 2 again. And cosine of 2 pi is 1, which makes that a 2. And let's see. Sine of 10 pi over 4 is the sine of 5 pi over 2, which is basically back to 90. So that's 1 again. And then just trust me, this pattern is going to continue for sine. Now we're going to graph this one. There's y, there's x. And I'm going to plot my points. So negative 2, 0. Pardon me, negative 2. Positive 2, 0. Got it. Root 2, 1. Root 2, by the way, is 1.414. So root 2, 1 is about there. 0, 0. Now, before I go any further, I'm going to connect those dots and draw a little arrow to show what happens. Okay? And then negative root 2, negative 1 is here. Negative 2, 0. So I came up here. And then negative root 2, positive 1, back to 0, 0. And then I came here. And then root 2, negative 1, back to 2, 0. And I get a little infinity sign. And that's how you graph parametrics. So parametrics exists for lots and lots of reasons. One of them is you can get non-functions. Okay, you can get things that are relations where x is a function of t and y is a function of t, but x and y are not functions of each other. And you get some pretty nifty looking graphs. You can get a parabola, that one up there is a sideways parabola, or you can get this nice figure 8, which is pretty cool too. Now, you can also graph these in the calculator and get like the really cool stuff from there. So if I back away here and we want to graph these in the calculator, it says graph each of the following in parametrics and marvel in the results. So let me show you how to do that. In your calculator, I am going to Control Doc to add a page. I'm going to add a graphs page. And then I'm going to figure out, wait, I can't graph parametrics in there. That just says function. So in the graph page, if you go to menu and you do graph entry edit, at least I think that's where it is. It is. Parametrics is choice 4. So menu, 3, and then 4 will change this into parametric form. Well, you'll get an x equals and you'll get a y equals. So if I go back, my x was t plus 2 sine 2t. Okay. And I want to be in radians. All right, so t plus, by the way, in parametrics, your calculator wants a t here, not an x anymore. T plus 2 sine 2t, and then y was t plus 2 cosine 5t, t plus 2 cosine 5t. And then down at the bottom, it has your t scale, your t window. And so right now, it's always going to default to 0 to 2 pi. 6.28 is 2 times 3.14. It's going to default to 0 to 2 pi. That's a pretty good place to start, unless you know your t-bounds are supposed to be something different. So I'm just going to leave them there. T-step is basically asking how many t-values do you want to see, and what it's going to do is it's going to plot a point every 0.13 for t. So it's going to start at t equals 0, then it's got to plot a point at t equals 0.13, and then plot a point at t equals 0.26, and you get the picture. So if I hit enter, look at that cool thing. It's so cool, you guys. And if I drag it, this is just like this crazy figure 8 thing. And if I change my t-bounds, it would just keep doing that. And it's like this crazy zigzag. It's so cool. And then if we go back, what else did I have you graph? 1.5 cosine t and cosine 30t. All right, so I'm going to arrow up there and turn this one off. And then arrow down. Oh, now my computer's freaking out. There we go. So it was what again? 1.5 cosine and cosine 30t. 1.5 cosine. Come on. There we go. I'm trying to express something for y. This calculator app is the worst. Oh my god, again. 1.5 cosine t cosine 30t. And again, 0 to 2 pi seems good enough for me. Well, that one's a little bit crazy. If I zoom in a bit here, menu, window, zoom in, you get that thing, which is just kind of crazy and not nearly as cool as the last one. And then last but not least, we have, ooh, this is crazy, sine of t plus cosine 30t, still in parentheses. And then cosine t plus sine 30t. Okay, sine of t plus cos 30t. Sine, oh my god, it's doing that thing again, of t plus cos 30t. And cos of t plus sine 30t. This one also looks bananas, but look at that. If I zoom in here, look at how cool that thing is. Now, one of the reasons I did this one is, I mean, A, it's just bonkers and very cool. But the other reason is, if I go back and I hit tab, and I go back into the graph, which I'm sorry that mine's jumping around so much. I'm going to come down here, and I'm going to change this 0.13 to 0.05. See how it looks a little bit smoother? The smaller your t-value is, the smoother your curve is going to look, but sometimes it just takes longer to graph. So if I hit tab one more time, and I change that 0.05 to 0.01, it's smoother still. Now, it didn't take that long to graph, but I mean, come on, you got to admit, that's really flipping cool. So that is the beginning of how we do some parametrics. Now, I need you to flip the page, because we didn't do any calculus yet. I just kind of explained, this is parametrics, and this is what they can look like. Now, we're going to do some very quick calculus with it. All right, so the calculus that we started the year with is, how do I figure out slope? How do I take the first derivative? And then right after that, we did the second derivative. Well, the first derivative has been defined as dy dx. Well, since we have a y equation and we have an x equation, if you want dy dx, or slope, of a parametric curve, you simply take the derivative of the y equation and divide it by the derivative of the x equation. And if you want, you can also rewrite this as y prime of t divided by x prime of t. It just means take the derivative of both. Okay? I'm going to explain the second derivative once we get to it. So just pause. You're thinking about that second fraction. I'll come back to it. Number 4 says, find an equation of the line tangent to x equals t squared minus 2t and y equals radical t, which is right here. And find the equation of that tangent line at the point where t equals 4. Okay? Well, let's see. One of the things I want to do is make a tangent line, just like we did before. And if I asked you 6 months ago, how do you find a tangent line? You should have all repeated back to me, xy slope. If you want a tangent line, I don't care if you are doing a series question, if you are doing a trig question, logs, or parametrics. If you want a tangent line, you need xy slope. Well, our x value is going to come from this x equation. So if I want the x value when t equals 4, I just plug 4 in. Logic prevails here. Then that's going to be 8. And then I need the y value. Y is the square root of t. So y is going to be the square root of 4, which is 2. So I have an x value. I have a y value. And now we need to find a slope. Well, if we want a slope, slope is dy dx. dy dx is going to be y prime of t divided by x prime of t. Well, y is t to the 1/2, so y prime, go away, y prime is 1/2 t to the negative 1/2. And x prime is 2t minus 2. So if I want the slope at t equals 4, that's going to be 1/2 times 1 over the square root of 4 divided by 8 minus 2. So that's going to be 1/4 divided by 6, which is 1/24. So my tangent line is going to be y minus y1 equals m x minus x1. It's exactly the stuff that you guys know already. You want a tangent line, you need xy slope. You want slope, it's dy dx. But instead of taking one derivative, you just have to take 2. That's it. That's it. Don't make it any harder. Now, part B says, is this line above or below the graph of this parametric curve? Well, if I draw a tangent line to a graph, sometimes the tangent line is above the curve, sometimes the tangent line is below the curve, and it has to do with the curves. Pete says, concavity. He's been sitting in my lap this entire time. Pete says concavity. Pete's right. Okay, so Pete the cat says you have to find concavity. Well, concavity is the second derivative. The second derivative in parametric, not quite so intuitive, so you just got to memorize it, okay? The second derivative of a parametric function is the derivative of the first derivative, and then you divide that by dx dt. So let me show you what I mean by that. So if I want to figure out what the concavity is, I need to find d2y over dx squared, okay? And if I want to find that concavity, I have to take the derivative of my derivative and then divide that by x prime. Okay, see how I did that? It's the derivative of the derivative. So the x prime is going to stay down there. Now I got to take the derivative of the thing on top. But it's kind of gross looking, so I'm going to simplify that a little bit. I could bring this 2 down to the bottom, and I could also bring this t to the 1/2 down to the bottom. So I'm really taking the derivative of 1 over 4t to the 3/2 minus 2t to the 1/2. Again, I brought a 2 down to the bottom and multiplied by it. I brought a root t down to the bottom and multiplied by it. Okay? And then I'm dividing that by 2t minus 2. And so if I take that derivative on top, I am going to think of it as a chain rule. I'm going to think of it as the bottom raised to the -1 power. So I'm going to do chain rule. -1, 4t to the 3/2 minus 2t to the 1/2 to the -2. Bring down the power, reduce it by 1. Multiply by the derivative of the inside, which is going to be 6t to the 1/2 minus t. All right. And I still have a 2t minus 2 down here. Now, I know it's ugly. You're not going to need to do the second derivative stuff often, if at all, okay? You might be asked to do it. So just make sure you understand the process. Now, we are supposed to evaluate that at t equals 4, which is going to be kind of annoying, but we'll deal with it. 2 times 4 is 8. 8 minus 2 is 6, so I got a 6 on the bottom. And on top, I have -1 times, let's see, 4 times 4 to the 3/2, that's 8, minus 2 times 2, that's going to be raised to the -2. And then 6 times root 4, that's 12, minus 4. And you know what? All I really care about if this is concave up or down, so I have a negative times a positive, raised to the -2 is still positive, times a positive divided by a positive. This whole thing is going to be negative, which means this concavity is concave down, so the tangent line is above the graph. Okay? Okay. Last little piece, right? This is the last piece. Am I right? I'm right. Last little piece here just says arc length. You've done arc length already. Quick reminder. Arc length from the old days is the integral from a to b of the square root as 1 plus f prime squared. If you want arc length in parametrics, it's seriously just the Pythagorean theorem. If you think about the Pythagorean theorem, and you might even want to draw this distance right here is a change in horizontal distance, also known as delta x. This right here is a change in vertical distance, also known as delta y. If I did delta y squared plus delta x squared equals c squared, and then I solved for c, c is the square root of delta x squared plus delta y squared. So the length of the hypotenuse is the square root of delta x squared, also known as dx, plus delta y squared, also known as dy, square rooted. That's exactly what we have right here. Arc length in parametrics is just a fancy version of the Pythagorean theorem. And effectively, what this arc length is doing is it's saying take that infinity parametric curve and make a Pythagorean theorem right here as a sum with a Pythagorean theorem right there, right there, right there, and then add all of those up. Now, at the end of the day, do you need to know all that? No. You just need to know the formula and use it, okay? So it says find the length of the curve above between the point 0, 0 and -1, 1. Okay, so I'm going to take the integral of the square root of dx dt, which was, where's my x prime? There it is. Dx dt, which is 2t minus 2, plus dy dt squared dt. I purposefully didn't put bounds in yet because your bounds need to match your letter. So I need t bounds. So I need to know what t value starts me at 0, 0 and gets me to -1, 1. Well, let's see. What t value starts me at 0, 0? Well, that's got to be t equals 0, I think. And what t value gets me to -1, 1? Well, it feels like 1. If I put 1 in up here, I'd get 1 minus 2. Yep, that's -1. If I put 1 in there, I'd get 1. So my t-bounds are 0 to 1. You just got to figure out your t-bounds based on your points. Then you just plug this in the calculator. And this is the last thing. I know this is a long video, but this is the last part. So I'm going to grab my calculator and open up a calculator page. No, calculator. Shift plus 0, 1, and then just be careful with your parentheses. 2t minus 2 squared plus 1/2 t to the negative 1/2 squared. Sometimes I get lazy and I don't want to do the 1/2. Completely acceptable to do the 0.5, by the way. Invalid data type. Why? Why are you an invalid data type? That's a great question. 2t minus 2 squared plus 0.5t to the negative 0.5 squared from 0 to 1. I have no idea what's wrong with that. Let's try it again using x. Again, I do not know what's wrong with it. 2x minus 1 squared plus 1/2 x to the negative 1/2 squared dx. An argument is of the wrong data type. I seriously do not know what's wrong with it. Oh, I know what's wrong with it, Mrs. Vibber. This is a Mrs. Vibber problem, not a you guys problem. I made a goober move here. I'm going to tell you what's wrong, but then we're not going to fix it, and I'm just going to promise you it won't happen again. We're starting at t equals 0, and if I put 0 into there, that's going to be 1/2 times 1 over the square root of 0. So this is technically an improper integral. That was just me being a goober. It doesn't like it. It can handle it. It does have an arc length, but your calculator can't compute improper integrals, so that's why it's having a beef with me right now. So ignore that part. Pretend it gave us a number, and then that number was 6. Sure, because I made it up. Okay? But it would regularly just go in your calculator. So not the best place to end a video with Mrs. Weber screwing up, but that's what happens sometimes. So I guess go me. You got one more video after this that I want you to listen to, and that's going to be lesson 2 on all this, which is on rectilinear motion. Before you watch that video, though, please try this lesson 1 practice set. The first part is just graphing things in your calculator for practice, and then after that, it's asking you some like derivative and second derivative kind of questions. All the answers are at the bottom of page 5. So happy mathing, and you'll see me again soon. Bye.